Hey guys, today I want to present a solution to the Estonia Team Selection Test 2019 problem 3. At first, let's have a look on the problem statement. We are asked to find all functions from the real numbers to the real numbers such that the equation 3 times the absolute value of y times f of x squared y is equal to f of x squared times f of y squared plus the absolute value of x times f of minus x y squared holds for every real number x and y. Since we have a lot of squares in our functional equation here and also have the absolute values, we are motivated to plug in the negative value of x or y into this equation here, because then only a few terms change. Especially if we take y to be equal to minus y in the equation, we get that 3 times the absolute value of minus y, which is also the absolute value of y, times f of x squared minus y is equal to f of x squared times f of minus y all squared, which is y squared, plus the absolute value of x times f of minus x and again y squared. And here we see that this is the right hand side of our functional equation, so this is equal to 3 times the absolute value of y times f of x squared y. Here we can now plug in y equals to 1 and x equal to the square root of z and get that 3 times f of minus z is equal to 3 times f of z. So we get that f of minus z is equal to f of z. This means that it is enough to focus on non-negative values for x and y in this functional equation here, and therefore this equation becomes the equation, I call it q of x comma y, which is 3 times y f of x squared y is equal to f of x squared f of y squared plus x times f of x y squared, and this should hold for every x and y from the non-negative real numbers. It is a good idea to plug in small values for x and y, and in this case the best choice is that we plug in 1 for both x and y and get that 3 times f of 1 is equal to f of 1 squared plus f of 1, and now we can bring the 3 times f of 1 to the right hand side to conclude that 0 is equal to f of 1 squared minus 2f of 1, and this is equal to f of 1 times f of 1 minus 2. Thus we get two possible values for f of 1, namely 0 and f of 2. So let's start with the first case, that f of 1 is equal to 0. Here we want to make use of the fact that f of 1 is equal to 0, and therefore we want one of our variables x or y to be equal to 1. So let's start with q of 1 and y, which tells us that 3 times y times f of y is equal to f of 1 squared, which is f of 1, which is 0. So this term is equal to 0, and we are left with a f of y squared. On the other hand, q of x comma 1 tells us that 3 times f of x squared is equal to f of x squared times f of 1, which is 0, plus x times f of x. And now we can use the first equation to get that this is equal to 1/3 times f of x squared. This implies that f of x squared is equal to 0, and now we can take x to be equal to the square root of z and get that 0 is equal to f of z, and this is also equal to f of minus z. This means that f of x is equal to 0 for all x in R. If we plug in f of x equal to 0 back into the original equation, we see that this is indeed a solution. Let's go on with our second case, that f of 1 is equal to 2. In this case, it's also a good idea to plug in 1 into this equation here, but before doing that, I want to do another step, because then this equation here becomes a bit easier to work with. Since the term f of x squared times f of y squared is symmetric in x and y, we know that if we bring x times f of x y squared to the left hand side must be also symmetric in x and y, and therefore our idea is to plug in yx into the equation, and we get at first that 3 times y times f of x squared y minus x times f of xy squared is equal to f of x squared times f of y squared. This is exactly this equation here, and now we use this equation again with x and y switched, and we get that this here is equal to 3 times x times f of y squared x minus y times f of yx squared. This yields that y times f of x squared y is equal to x times f of y squared x. At this point, we can now plug in y equals to 1 to get that f of x squared is equal to x times f of x. And here we can also directly see that x equals 0 yields f of 0 is equal to 0. With this equation here, we can simplify this term here to be equal to 2 times y times f of x squared y, which is equal to f of x squared times f of y squared. And now we can use this identity here for y to get that this is equal to f of x squared times y times f of y. Dividing by y with y is not equal to 0, we get that 2 times f of x squared y is equal to f of x squared times f of y. This means that 2 times f of ab is equal to f of a times f of b for all a and b greater than 0. b equals 1 over a then implies that f of a times f of 1 over a is equal to 2 times f of 1, which is not equal to 0, and therefore f of a is not equal to 0. Therefore, we can now write f of x is equal to f of x times f of x over f of x, which is equal to, now we use this identity here, 2 times f of x squared over f of x. At this point we use this identity here to get that this is 2 times x times f of x over f of x, and this is now equal to 2 times x. This equation here holds for every positive real number x, and now we use the fact that f of minus z is equal to f of z, and that f of 0 is equal to 0 to conclude that f of x is equal to the absolute value of 2x for all x in R. We can plug in this function now back into our original equation and see that f of x equal to the absolute value of 2x also satisfies this equation here, and therefore we found a second solution, and therefore we are done.